Well, hello, everyone. Today we'll be talking about maps, and that's kind of like an entertaining lecture. And I want to kick off today's session with like a very brief discussion. I want to do like a short breakout, and this isn't this is not one of those things that you can submit as an activity. Just like briefly discuss these two maps. There's a link that has been pasted into the chat by Han. I'll just do breakout rooms briefly for like 3 minutes. The left map here is something that Donald Trump tweeted. The right map here is like way more neutral, but I would like you to discuss both of these maps briefly in a breakout room. So I'm setting up breakout rooms now. Okay, here we go. Okay, it looks like we have everybody back. So those two maps, what are like? Let's start with the map on the right. What is going on in this map here?
The projection is not equal area.
Exactly. So we have a non-equal area projection, and what's the effect of that?
Stretches countries that are high up and low down in latitude.
Yeah, exactly. So we'll be hitting on this a lot today. This is what's called the Mercator projection.
Antarctica.
Exactly. And Antarctica isn't quite as big as it looks here, right? In this particular map, it looks like Antarctica is bigger than Europe and Asia and Africa combined, which is definitely not the case. Another country that's way over represented here is Greenland, right? Greenland is big, but it's not nearly as big as it looks here. So we have kind of like a problem here with distorted size. And now let's talk briefly about the left map here.
Nobody lives in the red areas. It's not faithful to the actual vote. You'd have to like scale the counties by size or by population. Scale the size by population.
Yeah. Any other comments about this?
I would say this is faithful because that is actually how those counties voted, but it's not equating consensus. I mean, you can't equate democratic consensus with geographical area, and that's what the map is doing.
Well, I guess it's correct that those counties voted like that, but I would argue that this map here is used to make a biased point, especially with the title, right? So it kind of like equates area with people's votes, and in that sense, it is definitely, in my opinion, problematic. Any other thoughts?
So I'm a geography master's student, so this is up my alley, but by drawing counties and equating that to the vote share, there's something that's called the modifiable areal unit problem. And It pretty much just says you can draw boundaries, and by drawing boundaries, your data representation changes with every different boundary you draw.
Yeah, exactly. So how do you slice up a space, the modifiable areal unit problem? We'll talk a little bit about this when we talk about Voronoi diagrams in a future lecture, but you're exactly right. So this is fairly problematic. And so we'll talk about these kinds of things today. And just to give you an example here is somebody has gone through the effort to take a map like this, Kerry versus Bush. As we all know, this was a very close election that Bush eventually won. But this map here looks like Bush really dominated. But in practice, if you actually look at the vote, it was that Bush won by 3 million in the popular vote, whereas the area, the red and blue shown on the map, is very disproportional. So this should kind of like remind you of the lie factor, right? The magnitude of the effect versus the perceived effect is very different. So that you could, like, using Tufte's arguments, you could say that there's like a massive lie factor in a map like that. However, this is like a very common problem with choropleth maps. That's what these maps are called. So, okay, let's take a step back. The principles of map visualization, maps are like a special type of spatial data that we all care a lot about and that we frequently use. We use maps when spatial relationships are really paramount. So like we have some kind of like entities like states or cities or something like that. And we plot stuff on a map if we really want to make sure that we understand the spatial relationships. Typical tasks on a map are to find a location, a feature, find a county, find a country, find a city, find a street, or route finding, like what's my best way to go from like Salt Lake City to San Francisco, or identify attributes associated with a location. For example, what's the elevation? Is it land or water? Or what's the GDP in, like, let's say, some kind of area that is identified by a map? And then you want to compare attributes between locations and features. And the one lesson that I want everybody really to like learn today is, like, whenever you think about, hey, I want to visualize something with a map, you should ask yourself first, do I really, really, really need a map, right? Because very frequently, like a map has a lot of problems, like as you just saw earlier with this political map. And for things like, for example, states of the US, if you are like a newspaper editor, the map really doesn't matter all that much because everybody has a good idea of where's California, where's New York, where's Florida, right? So you don't need to show that. People understand that very well. And if you use a map, you're also giving up the most important visual variable, that is position, right? You're giving that up to the position, to the location on the map. And that's okay if it's really the most important thing, but very often it is not. And so here's just an example of, like, actually one of my favorite all-time New York Times visualization. This is about how states, how like essentially the country has swung across different elections. And so here, like you see, like Utah is like a good example. In 2012, it voted overwhelmingly for Romney. But what you can do in a map like this, you can show the magnitude of like whatever the vote percentages was, but you can also show the whole history here, right? So you can go back all the way to 1952 and show exactly how these states have swung in various elections. And that's almost impossible to do on a map, right? And it actually wouldn't help us all that much, right? If we showed like where is Wyoming on a map and where is Utah on a map. So something like this is just like much easier done without showing a map than with showing a map. Oh, here is something else. This is like from like right after, like before we had final results for the 2016 election. And here we show like for different states, we show like a lot of information. Like we show how much of the vote was counted, what is the margin, what is the projection, what is the status, and then we show like uncertainty with these arrow bars here and these kind of like box plot like features. And so something like this is possible to do in a tabular layout or in any kind of other visual layout, but having so much information in a map is just not possible. So ask yourself when, like also when you think about your projects, do I really need a map? And if the answer is yes, then please go ahead. But if the answer is, well, actually, most people know the locations of these places that I'm trying to visualize, so maybe then it doesn't matter all that much. Okay, so now that I've caveated the whole lecture, let's talk about maps and how to visualize stuff on maps. And so the first thing that you need to know about is map projections. And so why do we need projections? And we talked about this a little bit when we had the D3 lecture on maps. But the problem is that, of course, the Earth is like not a perfect, but a slightly flattened sphere. And typically, when we look at a map, it is on like a flat display or on like flat paper or something like this. Of course, there's spherical displays, but they're very rare. And so what you need to do is you need to project or unfold the hull of the sphere to fit onto like paper or screen. And you, like in doing that, you will never find like a perfect representation, but you have to kind of like make compromises in how to unfold the Earth onto like a paper or screen. And things that you need to worry about is like, am I preserving area of geographic regions? Am I distorting shape? Is direction constant? Is the bearing constant? What is the distance between two points on the map constant? What is the scale, and so on? And I recommend that you guys take a look at this XKCD comic about what your favorite map projection says about you. My favorite one here is actually the globe. And so the simple solution for map projections is to just use a globe, right? And we can do that now if we have like 3D computer graphics. Here I'm looking at Google Maps. And if I zoom all the way, I have a globe, right? And the globe, I don't have to kind of like, this is like a perfect representation. Of course, with the downside, it's technically fairly challenging. And I can't see the whole world at the same time, right? I have to kind of like pick what am I looking at. I can't show like both, let's say, China and the United States in the same view without interacting. But if I can interact and if it's appropriate, then a globe is a great solution. so if you don't want to use a globe, you have to use some kind of projection. And like the classical projection is the Mercator projection, which was like developed in 1569. So it's a pretty old projection by Gerardus Mercator. And this is a projection of the sphere onto a cylinder wrapped around the globe. And what's nice about this projection is that it preserves the angles, and we have lines of constant bearing that map exactly the straight line. And constant bearing means that it's easy to navigate with a compass. And so that was kind of like super useful for sailors. And here's this example from my first slide here. This is like a Mercator projection of the world in D3. And of course, it has these kinds of problems. But one of the benefits is that it also like maps circular shapes to circles. So here is a Mercator projection of the Mars, and you see these circular craters, like the shape here is nicely preserved. So why is Mercator problematic? Well, we talked about the fact that it distorts area, but it also has some kind of like ethical implication. And especially this was used to teach geography frequently. And the problem, as we already mentioned, is this massive distortion of area distant from the equator, which makes it unfair to the global south and making places that are mostly trees, snow, and better off white people look huge, and the places where most of the world's population lives look puny. And so here's another quote. Mercator works really great if you're, say, Ferdinand Magellan looking for a compass bearing that will take you around Cape Horn, because all of the latitude and longitude lines and angles in between lay out nicely and straight on the map like we experience them in real life. It also works well if you Google and you want a map image that you can neatly slice up into little squares that your server sends to a customer's browser. North is always up, your hometown doesn't look squished or slanted when you zoom in to it, and everybody's happy. But of course, the problems is that, like, I'm not sure were you aware, and until I kind of like studied this in more detail, I wasn't aware that Africa is actually like so huge compared to like you can actually fit all of Western Europe, all of China, all of the United States, all of Argentina, and all of India into Africa, spatially speaking, right? This is kind of like a bias that we have in our mental models by looking at projections like the Mercator projection. And so here is kind of like what it looks like if you overlay a Mercator projection with the true size of the country. And you can see that like the effect is most pronounced for countries like Canada, Russia, and Greenland that are way, way smaller than they appear in a projection like the Mercator projection. And so you can actually play with this. This is this Mercator puzzle website. So you can like take a country and like move it around. And this one here is actually easy. What country is this?
Canada.
Canada, eh?
The Bay of Fundy, right? And see how if I move it around, how the projection changes the shape here. And then I can map it, lock it into Canada, and it's green. And so this here, that looks like Brazil to me. Let's see, it fits perfectly. And see, like if I moved it up to Canada, Brazil is like not much smaller than Canada, right? If you overlay it, but it looks much more smaller because it is close to the equator. Let's see, here we have a country that has like a hole in it. That's probably South Africa. And if you look at South Africa compared to Canada, it's pretty sizable, right? But down here, it looks fairly small. So yeah, play around with this to get a sense of these relationships. So the caveat here is what I'm saying is really only a problem if you look at very large areas like the whole world or continents. The distortion is not a problem here on a state city level. So like, for example, Google Maps using a Mercator projection is totally fine, because what we mostly look at if we look at Google Maps isn't like what is the relationship between Russia and the United States. We look at like, how can I like go to the car repair shop or this coffee shop? And so at this scale, a Mercator map is not problematic. An alternative idea would be to just like take latitude and longitude and map it, right? But this isn't like a nice map. This does not preserve angles. It does not preserve areas, and things are pretty squashed at the bottom and the top. And so that's something that is sometimes convenient if you just have latitude and longitude data and just want to plot something. But typically, that's not something that you do if you do some like more serious mapping. Another type of projection is the azimuthal projection. Here, you project you take a tangent and then you on the Earth, on the sphere, and then project this onto the Earth. That makes it nice that angles are correct around the center of the point, and you have great circles that go through the center are straight lines. And this is something that you would sometimes find like in an airline magazine where their hub is kind of at the center of this projection, and then all of the planes radiate out from that. And so here's like an example of an azimuthal equidistant projection in D3. And here you can see how this has been used, for example, in Time Life magazine to show where their reporters are on assignments and where they're moving around. Just some examples of these projections. And then we have a projection that's called the Winkel triple projection, which is a modified azimuthal map projection, which is averaged to a cylindrical projection. And so like how this works is they essentially take this ITOF projection, which is a modified azimuthal, and then take the mean between this projection on the right and the projection on the left to create this Winkel triple projection here. And the Winkel triple projection is called Winkel triple. Triple is German for, well, it's just a German spelling of triple. And the idea here is to minimize three kinds of distortion: area, direction, and distance. And this is now considered the gold standard of teaching geography. It's endorsed by the National Geographic Society, and that's what you would use in textbooks, for example, if you want to like teach kids about like maps in the of the world, then you would use like a Winkel triple projection. And so here you can see that like areas like from what we saw earlier with the Mercator projection, we can see that Greenland is still probably a little bit bigger than we wanted to, but it is not like as dominant as it was in the other projection. And so here we can see like if we have circles of equal size mapped on different places on this Winkel triple projection, we can see that like right in the middle on the equator, it's still a little bit smaller than up in the north, but it is much, much less pronounced. But we do have this distortion effect that is going on. Albers equal area is a projection that is very common if you want to like show a map of the United States. This shows areas correctly and distorts distances and shapes. But in practice, if you have something like Google Maps, as you earlier noticed when I zoomed out, is that we actually have composite projections. So like here we have like a map, and there's like a diagram down here that we can use to navigate different projections and different aspects. And so we can transition into different types of projections. And the further we have these kind of like projections that are optimized for that particular perspective that we're looking at. And then if we go in further and further and further and further, like here now we are in Mercator land. It's eventually like when you look at something like fairly closely. And so I think that's kind of like a neat way to illustrate like what are good projections for particular kind of like position or like perspectives on the Earth and zoom factors. So as we talked about in the D3 lecture, there is a ton of different projections that are available to you in D3. So just like review them. This also was just like a flavor. So if you're like a geography student, like then you will learn much more about this kind of stuff. But this kind of to get you started and thinking a little bit about projections. So one other idea is to like maybe not even like try to map it onto like a continuous sheet of paper, but kind of take more of an orange peel approach. So when you peel an orange, you break it somewhere. And so you could do something like this. And so here's like a video of like that was made for a paper that shows you how you could break up like the globe with different kind of ways to slice it. And these are all geometric shapes, but you can also do like smarter shapes, like for example, breaking it up along lines that are only in water, which as you will see at the very end. So here, this is broken up by mostly water. And now you can also break up by mostly land, which is then leading to a very unintuitive map. Okay. So this here is like a link to a pretty good treatment on projections. So if you want to study more like on projections, just go to this website and there's like a lot of information there. Great. So then I want to move on a little bit to map software and navigation. So mapping software, we have tools like OpenStreetMap and Google Maps that we like use frequently in our like modern like smartphone is always on lives. And so here we can like use navigation features, and navigation can be in the abstract or in the specific spatial realm, right? So here's like from work to go for an after work beer to the Porcupine. I can either drive or I can walk. These alternative routes are shown to me, and alternative routes are shown to me on this map in something like Google Maps. I have kind of like abstract walking, or in this case, like bus directions that give me timing information. And on the right, I have the specific, this is the route that I have to take. And of course, where am I? What is my heading? And so on. So all of this is very useful. But if back in the day, before we had like GPS all the time, we would draw maps. And if we actually describe like to other people how to navigate to a specific point, we do something very different from what Google Maps does. We kind of like give landmarks and have rough description and really distort stuff. So for example, we say, yeah, go straight this road and then turn right at the Wells Fargo or something like that. And that's not usually how mapping software works, but some people have tried to kind of emulate this. This was like a paper from 2001 by Microsoft Research. And they asked like, okay, if I want to like navigate from Madison to Kalamazoo or whatever it's exactly called, what would be kind of like a human-like representation? And they came up with the solution that you can see here on the top, which kind of like expands regions where you have to have make multiple turns, and then shortens regions when you're like just going straight on the interstate. So it's kind of like emulates human-like directions. And this was actually implemented in Microsoft Maps, which is now defunct, but never really caught on. And I think that part of that is probably because we have now these like real-time navigation systems, right? And we don't really look at these kinds of maps anymore. If we want to navigate, we just get turn-by-turn instructions for navigating. Okay, so now like this was just the general stuff about maps, and now let's get started with thinking a little bit about how can we map data onto a map. And so the simplest way would be like direct mapping. You have like one data point that has spatial parameters, and then you put one pixel in for that data point. And that's something that you can do easily in a Google map. And so here, this is a map that where you can actually zoom in and resolve individual addresses. And this is somebody has kind of like scraped public records and mapped the location of every gun owner in New York State. I think it was New York State. And that was a big scandal back in the day. This was in 2013, right after a shooting. You could zoom in and you could see and check whether your neighbor owns a registered gun or not. And it ended up being like a big scandal, and I think that the people that published that map got into trouble with their jobs. But I wanted to kind of like ask you all, do you think like this data is public information, right? Is creating a map like this responsible, or is this problematic? I hear it's a bad precedent, or it depends. So what does it depend on?
Depend on what like if it's info that would be beneficial to public benefit for it to be known, which I'm not going to get into what that is because I don't want to get into politics on here. But if it's beneficial for it to be known to the public, then I think it would be responsible. So
yeah. So the point I want to hit here is when we create a visualization, we change the accessibility of data, right? Just because something is public record is not the same as, let's say, like court in Utah, for example, all kind of court documents are public record. It's very different from like having that in a public database and publishing a map of all of the court cases all of your neighbors had in your particular neighborhood, right? You kind of have a responsibility to think about the consequences of what it is, like how you're making it accessible or not. And so it is often like a difficult judgment call to do this kind of thing. I see like somebody wrote, information is neither good nor bad, it's what society and do with it that makes a difference. Yeah, I think that's a perspective. But it is more complicated than that. But yeah, maybe we're getting a little bit too deep into ethics here. But yeah, just think about like where is the line, even if a data set is public, as somebody who creates a visualization and therefore makes it super easily accessible for somebody that doesn't have like a strong motivation to look at something, that changes a little bit how the data, what you can do with the data. Here is like basically this is kind of like a map that by XKCD where we have kind of like this isotype approach. We represent like not every data point is a person, but every kind of like 250,000 are represented by a little glyph. And so now we get a better sense of what is the distribution of people across states and how have they voted. And for the 2016 election, we see that there's like one blue, one green. This is like other candidates and 2 Trump voters in Utah, for example. And that's kind of like probably a more accurate representation of how people have voted within each state. So one of the most common things, because it's so easy to do, is these choropleth maps. And choropleth maps are really this like areas are shaded or patterned in proportion to some measurement, and then the spatial units are filled with a uniform color or a pattern. And so that's what we saw earlier in this kind of like map that Trump tweeted. We have pretty early examples of that. Here is kind of like a map of French districts and illiteracy in these districts in a choropleth example. And of course, it's kind of useful to highlight these spatial trends. And of course, the big problem with all of these kinds of mapping exercises is that geographic profile maps or choropleth maps are basically just population maps. And so like if you do something like this, you really have to account for population density in specific areas. And population density, as we all know, is very unequally distributed. So you see here, which I think is also kind of like a neat 3D map, where are people living? And we see kind of like the familiar picture that like the coasts are pretty like densely settled, and then there's like east of the Mississippi, there's generally like it's generally more densely settled, but then in the Great Plains and in the west, we have kind of like these beacons like Las Vegas or Salt Lake City or Phoenix or Denver, but then the country here is really very sparsely populated. And you could try like one thing that like another thing that this map that we saw at the beginning, what they did wrong is it didn't show you a percentage of the vote, right? It just showed you an absolute who won, but not by how much. So it kind of like lost nuance there. you could just add a little bit more nuance to a map like this by showing the percent of a vote for a particular candidate, right? And then now you can see that it's not quite as dominant anymore, and we have a lot of kind of districts that are either light blue or light red, and it's not quite as divided as it looks. But you could also like do that by population density, and then you get like a map that if you wanted to show something on a map, I would argue that this is a fairly responsible map, right? Because here now you have the white space, and you get a better sense of where did people actually vote for which candidates, and how many people do actually live there. So another approach to do that would be, like, of course, one thing that you should always do is if you do something like mapping, you typically don't want to show absolute values. So here on the left in this map here, we have the there's like a crime, a type of crime in Canada that's called mischief. Mischief is like a minor crime, non-felony crime, right? And here on the left, we're mapping how many of these mischiefs have been kind of handled in Canada. And what we see here is that like Ontario and maybe British Columbia and Alberta, but mostly Ontario, they seem to have a ton of mischief. But of course, we're not accounting properly for population here. And so what you could do instead is you could just like normalize by population. And so that's what we have here. And the problem with this is that, well, now we see that Ontario actually doesn't have all that much more mischief than usually. But like I think this is Saskatchewan, if I'm right. So there seems to be like a slightly increased rate of mischief. But then there's like the northern states or territories that have like seemingly a ton of mischief. And so anybody have a hypothesis what's going on here?
Since there's so few people, like even like 1 or 2 mischief counts could make it seem like a high percentage.
Exactly. So we have small numbers kicking in here. There's very few people in these areas. And so if you account for that, you can calculate what these authors here, Michael Correll, calls a surprise map, right? And so you can see that like they now don't show like mischief rate, but what they call sign surprise. So how much would you expect given the data of this, and also taking account for variability when analyzing small numbers. And that's a very important lesson, that you, like when you have small numbers, you kind of get weird outlier effects. Like one classical example of that is that people historically thought that small schools lead to better outcomes, like in terms of grades and education and so on. But it turns out that small schools just like have much more variation. And so that this is actually in effect, like the small schools have the best outcomes, but they also have the worst outcomes. And on average, the size of the school isn't really predictive of the outcomes. And so that's something that you just have to be aware of when you map something like this. And this paper here shows like a way of doing this for maps. And so you can see that essentially we have slightly more kind of like mischief happening in central Canada and less than we would expect in Ontario and Quebec. And if you, this is like, here's an example of this for unemployment. So if you just plotted unemployment rate across the country, you will have some kind of like small, you will have effects of small countries like counties like here, for example. This seems to be kind of like weird. Why are there so many unemployed people here in the Upper Peninsula of Michigan, or roughly here, like in Montana? But yeah, again, here there's very few people that live in these areas, right? And so if you kind of calculate a sign surprise map for this, you get a better picture. You see that actually in much of this kind of like Midwestern areas, you have actually, there's unemployment isn't that big of a deal, but you have pretty massive unemployment here in Michigan, and then you have pretty massive unemployment in kind of like Southern California areas. So these kinds of things, they suddenly fall out if you are more careful about like how you calculate the measures that you're then actually visualizing. Here's just a fun map of like bear density in Finland, visualized as bears. People have like done this. What are kind of like favorite sports teams in certain regions? And so I see that Garrett is asking, how is science surprise calculated? I would refer you to the paper. They have the details in there. I don't recall exactly, but I'm pretty sure they have some kind of like filter function for small areas. And I'm linking to the paper. Yeah, thank you, Haihan. Great. So like here we have a map of like baseball allegiances by users. How could you get this kind of data?
Social media.
Exactly. So lots of people are proud of their teams, right? And they make this available in public Facebook profiles. And this is like a New York Times project that actually scraped this from public Facebook profiles. And so you can see some interesting things here. You can see that like Red Sox and Yankees territory in the Northeast is pretty well kind of like delineated, right? There isn't really like much of a transition period. It's kind of like New England versus New York. It's also quite interesting that like you have in sports like basketball, you have certain teams like the Lakers that are very prominent outside of their core markets, right? So you can actually see here that the Lakers geographically dominate in Canada, and it's kind of interesting, right? That like the Raptors is like the Canadian team, and it's not like British Columbia, for example, or even Quebec, which is fairly close to Toronto. They prefer the Lakers over their own Canadian team. So it's kind of interesting to see these different effects on a map like this. And so this is like a really cool project by Bloomberg that I wanted to highlight a little bit. Let me go to this website. So this is about land use. And this is, of course, a nice use of a map because it actually perfectly, like how is land used maps perfectly to a map. So we can look at this. We have these kind of classes here: pasture, range, forest, cropland, special use, miscellaneous, and urban. And so we can see that urban is actually fairly small, and miscellaneous is not all that well defined, but special use usually means military. And so you could see like in like here, like west of Salt Lake City, we have like a big military range, and then we see this like these three blue elements here. But on like this now shows it on a specific map, but we can kind of like rearrange this to kind of get a better sense of like what are the proportions, right? So here we can see that like not quite half, but maybe a third of the United States is used as pasture or rangeland, whereas like a big sizable portion is used as forest, and then we have like a massive amount of acres that are used as cropland. And then urban is actually fairly small. Like all of urban area would fit into kind of the northeastern corner. You can like browse through this and look at individual aspects here. And then in this case, like they're now showing us this is a tree map. Like here, well, we have state parks and defense and wilderness areas and so on that are all kind of like summarized in this blue. Here we have agricultural land, so you can see where is agriculture dominant and how much does this make up of the United States in total, and so on. So take a look and read through this on your own if you're interested. Okay, so in addition to Choropleth maps, we have proportional symbols maps. And so these are kind of like a nice alternative. Here you use a symbol instead of a color, and you scale that symbol according to some data. And that accounts a little bit better for these kinds of variation in population density. And so here's like a classic example. This is like, instead of coloring these counties, they are scaled by how many, like these bubbles are placed in each county, and the bubbles are scaled by how many people live in a particular county. And what you can see here is that this gives like a more nuanced picture of what is going on when people vote. But of course, there's a little bit of a problem still, because certain very densely populated counties, like around Chicago, for example, or around New York City, there's a lot of overlap. And so you need to use transparency, but even then it's not all that easy to resolve. This was a map that the New York Times made to show how much states have swung after, like, from the 2012 to the 2016 election. And you can see that we have this massive swing to the right towards Republicans in especially like the Midwest. And the only state where we can see like a very dominant swing to the left is actually Utah, which is a little bit counterintuitive, but that kind of makes sense if you think about it, that Mitt Romney was way more popular in Utah when he was up for election than Donald Trump was. And so that's kind of like just another kind of symbol. You don't always have to use circles. You can also use other glyphs like arrows here, or directed arrows here. And then here, this is kind of like a different idea that uses a glyph where you have these triangles, and the triangles, the height is scaled by the total votes cast, and the width is the margin in net votes. So this is a little bit harder to read, in my opinion, but also makes for kind of like an engaging and interesting map. And I did show this this map in like one of the introductory lectures that shows you kind of like the diaspora of Katrina, where you have these proportional symbols where people moved to when they moved out of New Orleans. And of course, here we run more into this problem of overlap, because what we can see here is that people don't mostly moved regionally, but also moved to other urban centers in the US. Here is like, where do people donate, and overlaid on a map of Manhattan. So you can see that like seems like they're on the west side of Manhattan, west of the Central Park, there's more Democratic donors than there is on the east side of the park. But of course, these circles, they have been kind of made fun of, and so yeah, just be mindful. They're a better tool than Choropleth maps most of the time, but if you get overlaps, then it might become problematic. Kind of like a niche but interesting idea are these fat fonts. And so fat fonts, they use like an explicit glyph, like for a number, to represent a data point. And that glyph is designed such that it corresponds, like the black area for each number corresponds to the magnitude. And so you can see that the 1 here is mostly white, right? It's a very skinny 1, and the 9 here is very, very black overall. And so it kind of corresponds to like, this is very dark. And if you then do elevation maps like that, you can kind of like get these neat effects that you see, okay, here is something that is like, there's a peak, and you actually represent this by using real numbers. And I would say this is almost more of like a design and not necessarily a data visualization thing. So it's kind of like data art, but it's kind of like still a cool idea. And they do this also in a nested way. So if you want to visualize 489, they designed this font so that it's exactly proportional to the data that you're representing. And there's like they actually, this was an HCI research group, but they also made maps of the world, for example, that show you population density, and you could explore them, and you could even order these maps. Okay, so the next type of maps that we want to talk a little bit about are contour maps or isopleth maps. These are fairly common. For example, here we have a map that shows lines of equal magnetic declination from 1701. Again, useful for, of course, navigation. We use those also to show elevation changes on top of maps, things like hiking maps, right? So here you can count of like how many contours do I pass when I'm hiking to kind of like estimate or calculate how much elevation change you'll have to go through for a specific on a specific hiking trail, for example. But we can also show these contour maps to, for example, like this is fairly common to show path of hurricanes and kind of like cones of uncertainty. So like you have like your main predicted path of your hurricane, but then in this area could also like be that the we're not sure what exactly within this certain contour. We think there's like a 95% chance that the hurricane will be somewhere within the contour shown on a map. So cartograms are the next important type for maps, and cartogram kind of again try to address this size versus data effect that we talked at the beginning, and they do it differently from let's say proportional symbols or using transparency or anything like that. They're simply trying to like distort the area to kind of map it to the magnitude of an effect. And so this is kind of like a compromise between geospatial accuracy and the quality of the data encoding. So here is a map that does this, like a historic map that does this for shows the population in 1916, and you can see that like big countries by population here are like also represented as pretty big squares, and they are roughly placed on where they are located. So we can see, for example, like we see like China and India, of course, are roughly where they are in Asia, and then Canada, which has like a relatively small population compared to its size, is still like north of the United States, but it is much smaller. So these maps are pretty smart, right? You kind of get a sense of where things are, and you get a sense of how the proportions are. Of course, they break down at some points. So if you were to, well, here's another example. This is a recent one from our World in Data. It shows us the world population in 2018. And it doesn't use these kind of like bigger rectangles, but it uses smaller rectangles that are kind of like scaled and that you could still count. And we're getting a picture that is actually fairly similar to a map that we would be used to. But I guess the big difference from what we are used to is that Russia and Canada are almost like way smaller than we see them on a map. But otherwise, this is kind of like a useful map and gives you like a good sense of what's going on in terms of geography. So you could also do this in a more extreme way. So here is like a map of the world with a Choropleth map. And now I could kind of try to scale all of this by population with some kind of like fancy distortion algorithm. And so you would get something like this. Or I could scale by GDP. And what you see here is like, this here, I guess, works somewhat, right? Because big countries often have big populations, except for Canada and Russia and some other northern countries. But here, if you scale by GDP, you suddenly get like very, very strongly distorted. So here I would argue that you're very much losing geographical context, right? It's kind of like you can't pick apart countries in, let's say, Eastern Europe or Africa anymore. Or if you scale by child mortality, we get these very different maps. They kind of like make a point, but they're kind of also very weird to look at. Or greenhouse gas emissions. And this was like a map, Kerry versus Bush of the United States. And I would argue that this isn't a map that I would show to people, just because it's not all that valuable, right? I don't really have good geographical sense here anymore. More modern takes on this are these kind of like abstract representation. This is from the 2018 House elections. And so here each state is represented, like each congressional district in each state is represented by a single square, and then for each of these squares, you get kind of like the predicted or the final winner or whoever is ahead. And so these maps are, in my opinion, super smart, right? They kind of like give you a geographical sense. You know where to look for your state, and they show you the proportions roughly. So notice that, for example, in California, you have kind of like it nicely separates the urban area, like even within the states, these rectangles are arranged roughly where this the location is, like where the people are that voted like that. And so a lot of news outlets have now adopted these kinds of maps. Here's a different one that from The Guardian that uses like hexagonal bins instead of squares, which I also like a lot. And here's like a comparison of different maps. Like you have The Guardian on the left, you have like the Axios map, Bloomberg map, New York Times, Politico, and Washington Post. And if I look at all of these, I would maybe say that my favorite here is kind of The Guardian. The hexagons, they make for like a nice geographical shape, and they are also like nicely placed. They're aesthetically pleasing and they're faithful to the data. So these are kind of like really cool ways to show something like in a geographical context that is otherwise tricky to show without biasing this a lot. Okay, so flow maps are like an example. If we have things like, for example, trade between different regions of the world, we sometimes want to show that on a map. Here's an early example of a flow map. This is where people like they commute to or like travel in Ireland, and so you can see that this is kind of like radiating out as a star more or less from Dublin. One example of a flow map that we already discussed is kind of Minard's depiction of Napoleon's march on Moscow or in Russia. And so here you have this kind of like the flow of the army in a geospatial context, visualized how strong the army was at that particular point, and all of that put together with additional information such as temperature and so on. So as I said, this is like a cool map. You also have these kind of like wind maps that are kind of like related to what we had earlier with like the magnetic declination, but you see the flow of wind on the oceans, again, useful for navigation. But there's also modern versions of this, and this is kind of like a nice project that gives you live data about where, like, what wind patterns are currently prevalent in the United States. And so you see that, like, right now there is the major pattern seems to be like somewhere in the Great Plains region. We have this kind of like interesting pattern. And they also have a gallery of major events, like, for example, Hurricane Sandy. Like that is historic data now from 2012. And so you can see how Hurricane Sandy kind of like was, where it was, how strong the winds were, and that the rest of the US was basically unaffected. You've probably seen this kind of like in high school science or geography classes. Here, like, how do countries trade with each other? This map here shows, for example, cotton trade before and after the Civil War. So you can see that there was like a lot of cotton trade between the United States and the UK before the Civil War, but after the Civil War, the UK has mostly kind of found different sources for cotton, and that we don't actually see, but I'm assuming like it looks like somewhere in Asia. And then you could visualize these kinds of flow maps, of course, on top of for population. So here is like an example of showing migration on top of a map. And we could pick something like Salt Lake City here and see where do people come from or where do they move to. So inbound is blue and outbound is red. And we have like a multiple view up here that shows us like the overall sum. This is from 25 to 2010. And so we see, well, it looks like people move to Salt Lake City from like all over the place, but maybe a little bit more from the West Coast than from the East Coast. But it's not like all that easy to see, right? If we look at different counties in Utah, it doesn't look, or around Utah, like there's people from Park City like moves. It looks like people from like California tend to move to Park City, but there isn't all that much migration here. Kind of a different non-spatial representation of a similar data set is this one here. So this is a more recent piece from the New York Times. And so here you can like pick any state, and let's go to Utah. And now, because we kind of like don't have the spatial context anymore, we can like add additional dimensions in our visualization. In this case, we are showing like historical data. And so we see that like for Utah, where people born in Utah have moved to, it looks like historically around 1900, 80% stayed in Utah. Nowadays, about 70% stayed in Utah. And 1940 to, let's say, 1990, like a lot of people moved to California, but now more recently, more people move to other states in the West. If we switch this of where are people coming from, you can see that like there was a lot of immigration from outside the US around 1900, and then that kind of died down around 1940 and picked up again around 2000 or 1995 or something like that. And so this here is like for every single state. And what they do pretty well here is they kind of like give you like levels of detail very smartly. So for example, here, if you look at West Virginia, you see people from Ohio or Maryland, but then for like rare states, they just like summarize as other states in the West, right? Otherwise, they would have like a ton of little lines here that wouldn't be all that easy to see. So a lot of cool data abstraction going on here. And here is a flow map that shows us kind of like where, like how much freight is being shipped on rail in the United States. And so we see that there's like this this dominance of the central area here, which I suspect is probably due to some natural resources like coal or something like that. And then you can do flow maps also for like movement. You kind of see this sometimes for birds, but this here is like a visualization of flight traffic in France. And so each of these kind of like lines that light up is a plane with a little bit of a trace. And you can kind of get a sense of like in the middle here, we have Paris. And they kind of like show a couple of different like interaction techniques. And then you can also kind of like drop this into like, since flights are three-dimensional, you can move from 2D to 3D dynamically. And so you see that you have these layers and work like at set altitudes that airliners travel in. Okay, so well, we have 15 minutes. I want to do an activity, so I'll keep going for 5 more minutes, and then we'll do the activity. Great. So we can also do data-driven maps. So far, we've always used some kind of like geography, like a GeoJSON file or something else, and then mapped on top of it. But we can actually, like, if we have enough data, we can just show the data directly without any map behind it. So we can just show, for example, like the central location of every zip code. And we get a pretty good idea of kind of the shape of like the United States in this example. Or this project is very cool. That is about, this gives you like a dot for where people live, and the dots are colored by ethnicity. And so you can see that like roughly we have like the north, or the kind of like urban east, the countryside in the east is very blue, but then you have like the south has a lot of black people. And if you zoom in into, let's say, Utah, this is very detailed. We can look at Salt Lake City, and we can see kind of like the pretty strong segregation in Utah, right? So you essentially have on the east side, you have like all white people. On the west side, you have like mostly Hispanic people. And so you can actually see this kind of like segregation happening across the country whenever you zoom into a city. And this is a map that like zip codes are ordered. And so like you could just like, this is the map that you would create if you just drew a line for the central location of every zip code in order. And then you get what this guy called the zip scribble map here. Here we have like taxi drop off in New York. So you can see that taxis tend to like drop off a lot in Manhattan, but of course you can also see the other districts, and you can see like basically the street grid completely emerges from just these taxi drop offs. And then here, this is an example, and I'm going to skip over this video today. Let me just look at how much do I have left. Well, I don't have a lot left, so I'm just going to wrap this up, and then we'll do the activity. Here, this is just like mapping data, and like there's a link, the video behind here. I'm going to skip over the video today, but the idea here is that if you have, for example, data about people, you can just point it, but then you can rearrange it dynamically. For example, dynamically morph a bar chart into a map by simply plotting it in a scatter plot of latitude and longitude, and then color coding it by something. Maps are, of course, not limited to like geography, right? You could also do a map of like an indoor space or any kind of like geographical area. Here is like a map of how people that like spend an hour in front of the TV, how they moved around, like humans and also animals or pets in this case. And then maps are often also kind of like not used actually as real maps, but more as thematic maps. So their map here is really just an analogy. We don't actually have an, like geography behind that. And so one good example of this is kind of like the internet in 2007. If it were a map, you have like MySpace land and AOL and Facebook land, which is still tiny. And of course, this is kind of like, looks like a map, but is not a map. Here's like the 2010 update, and suddenly Facebook is dominant, and Twitter and YouTube are starting to appear. But you can also, like, there's tools to automatically create these kinds of maps. So Stephen Kovarov, who is at Arizona, he's kind of like created software to create these maps based on certain topics. So this is kind of like, what are television shows like, right? He has like the Premium Peninsula on the left with kind of like all the HBO content, the political left bank, political right bank, then the toddler land, middle land, and so on. And so, but just by analyzing similarity between different television programs, he kind of creates these maps with clusters that are kind of evocative because they look like a real map, but of course don't represent any real geography. Okay, so that kind of wraps it up. And now I want to do this activity here. We like have a COVID dashboard that includes a map. And so this is kind of like the very like popular John Hopkins COVID dashboard. Hi, Hanor, you posted the link to this. And now I'll set up breakout rooms. And like, please use the last 10 minutes to answer the questions in about this map. And then I'll not have people come back today. So when you're done with discussing it, you can just sign off, and then we'll discuss it at the beginning of the next lecture. What are the kind of the properties of this map? Okay, so let me set up the breakout rooms. And thanks, everyone. And then remember, next week is the VIS conference. Please make sure that you attend 2 sessions. We'll still be sending you recommendations. They just put the program online. Okay.